Well, with the end of our study on waves, we now embark on a whole new adventure into physics, that of electric fields and electrodynamics. To get started, we need to make a few definitions: insulators and conductors. Conductors are materials in which electric charges flow quite freely. Examples are metals such as copper, aluminum, silver, gold. These metals have an outer valence that is very, very small, usually just 1 or 2 or 3 free electrons, and they can be shared equally through the material itself, and that allows them to conduct electricity very well. Insulators are materials that do not readily transport charge, so they don't have a small outer valence, and also they may not have a good lattice structure in which they can share charges easily. Examples are glass, rubber, plastics. Glass and rubber being amorphous, they don't have a nice regular structure that allows the electrons to be shared easily, and that makes them poor electrical conductors. Semiconductors have properties between insulators and conductors. They have an outer valence that generally is about halfway full, and if you dope them one direction, they can get a little bit above halfway, and then they become conductors. And if you dope them another direction, they can become a little bit less than halfway full, and they become insulators. So with a little bit of doping one way or the other, they become conductors or insulators. In electrical sense, you could say that they are on or off, or in a logical sense, you could say it's yes or no, 1 or 0. In other words, semiconductors are great materials for bridging that gap between a logical decision between a yes and a no. Hence, semiconductor materials are great for logic gates and ultimately for computer applications. We could have put another line in here for superconductors. Superconductors are conductors that conduct without any resistance, and by doing so they can also store energy in a magnetic field indefinitely without loss of energy, as long as they are in the superconducting state. So those are great materials. I only mention that because that's what my background was in superconductors, but I'll just get a short mention of it right here. Properties of electric charges. Ben Franklin has been credited with being the discoverer of electricity, so you should know that. Also defined negative and positive charges. Found that like charges repel and unlike charges attract. Here's an example. If you took fur and you rubbed a rubber rod, you would impart a negative charge to that rod, and if you brought two of those close together, you would find that they would repel. And there would be, in this particular setup here, there would be a torsional turn to the suspended rod, and you could measure that torque, and you could measure the force responsible for that torque, and so you could come up with some kind of experimental relationships on the force of repulsion in this particular sense. And on the other hand, you could take a glass rod and rub silk on that and impart a positive charge to that. And if you bring that close to the fur-rubbed rubber, which has a negative charge, then you would see that they were attracted. And you could measure that force of attraction, again, measuring the torque and extracting the force from that. So you can come up with some relationships that help you to characterize this force. Millikan ran some experiments and found that charge is actually quantized, which means it is found in discrete bundles. It's not continuous. It is exact multiples of some finite discrete value, And that finite discrete value is what we call E, this little e, which is the smallest unit of charge that we'll deal with, and that is 1.6 times 10 to the minus 19 coulombs. That is the unit of charge, the coulomb. This smallest value of charge, this E, is the value of charge that resides on an electron or a proton. If it's a proton has 1.6 times 10 to the minus 19 coulombs positive charge, and an electron has 1.6 times 10 to the minus 19 coulombs negative charge. So those are the smallest values of charge that we wish to deal with. And we were saying that all other values of charge are integral multiples of this smallest value of charge. So this is a value you want to memorize. Millikan discovered this fact by his oil drop experiment, where he took an atomizer and created these small spheres of oil, pretty much about the same size, and they would pick up static charge in the air, and by applying different voltages, he could suspend these oil droplets based on their electric force against their own weight. And you would find that different groups would suspend at different voltages, and there would be discrete values of voltages that allowed this to happen. And based on that, he was able to surmise the value of this charge in discrete amounts. We'll take a look at this, or example of how this works a little bit later. But very brilliant experiment. There are, in fact, fractions of this smallest value of charge that we're not going to deal with ourselves. But if you took a proton and you smashed it, you would get pieces of the proton, which we call quarks. And quarks are little pieces. There are 6 of them in particular, and they could have charge of 1/3 or 2/3 of the E as you put them together and comprise a proton, electron, or a neutron. But we're not going to deal with that. They're too quirky for us, and we're just going to deal with the smallest value, E, which is the charge on an electron or proton. So you conduct experiments, and one observation you might do with these force experiments is you find that the forces between charges varies as the inverse square of their separation. In other words, as you separate these two charges, you find that the force drops off as the distance squared as you separate them. And this will just be an experimental observation. You also would find that the force is proportional to the charge on one object and proportional to the charge on the other object as well. So you just conduct experiments, and you find that if you add charge to one object, the force increases proportionally. If you add charge to the other object, the force increases proportionally as well. So these are just experimental things you can do, and you find out these relationships. You find that the force is attractive if the charges are of opposite sign, say a positive and a negative, and that they are repulsive if the charges are of the same sign. If they're both positive or they're both negative, then the forces will be repulsive. So this is what you do. You run experiments, you find these relationships, and you keep on running experiments, and you can't find any other relationships. This is it. So this is all you find with all the experiments that you run. So you're ready to form a supreme relationship. In other words, this all leads to Coulomb's law, where the force is equal to some constant, K electric if you will, charge 1 times charge 2 over the distance between them squared. And this is just combining the relationships that you found experimentally. You found that the force is proportional to one charge, it's proportional to the other charge, it's inversely proportional to the distance between them squared. And once you find those relationships, you put a constant out front, and then you have yourselves an equivalency or an equal sign between the two. This K electric is something we're going to redefine a little bit later as a constant that is related to a universal constant. It's 1 over 4 pi epsilon naught. And epsilon naught is the permittivity of free space. It is a universal general constant, 8.85 times 10 minus 12 coulombs squared per Newton per meter squared. And so that's going to be a constant that we're going to know pretty well later on. But if you put that value into 1 over 4 pi epsilon naught, you will get a value for K of 8.99 times 10 to the 9 Newton meter squared per Coulomb squared. For our purposes, we're going to round this up just slightly, and we're going to say that K is equal to 9 times 10 to the 9 Newton meter squared per Coulomb squared. So that's going to be your rule of thumb. Our K electric is 9 times 10 to the 9. Nice round number to look at, and that's what we're going to be using for all of our electrodynamics. Okay, let's try out this new law, this Coulomb's law, with a problem. Calculate the magnitude and direction of the Coulomb force on each of the 3 charges in the figure below. All right, so we have 3 charges here. We have 6 microcoulombs, 1.5 microcoulombs, and negative 2 microcoulombs. And the separation as well. And the fact that we have a 1.5 microcoulomb charge in the middle does not shield the fact that the 6 and the minus 2 are going to interact as well. So there's no blocking of the interaction at a distance. So there's going to be a force of repulsion between these 2 positive charges, and they're separated by 3 centimeters, and they're going to have an equal and opposite force pushing them each away, and the magnitude of that force is going to be equal to our K electric, charge 1, charge 2, over the distance between them squared. So this is going to be 9 times 10 to the 9. 6 microcoulombs is 6 times 10 to the minus 6. 1.5 microcoulombs is 1.5 times 10 to the minus 6. And they're separated by 3 centimeters. 3 times 10 to the minus 2 meters. Square that, and we get that is 90 newtons. So they feel a force of repulsion from each other of 90 newtons. One's in one direction, one's in the other direction. Between the positive 6 microcoulombs and the negative 2 microcoulombs, we also have a force of attraction. We're going to call that F2. The magnitude of that force is K, charge 1, charge 3, over the distance between them squared. K is 9 times 10 to the 9. Charge 1 is 6 times 10 to the minus 6 coulombs. Charge 3 is a negative 2 microcoulombs, but we're just going to put 2 microcoulombs in there, 2 times 10 to the minus 6 for the moment. I'll explain why in just a moment. And the distance between those 2 charges is 5 centimeters, so 5 times 10 to the minus 2 meters. Square that. That's a magnitude of that force of 43.2 newtons. The reason I didn't put the minus sign in for the 2 microcoulombs is because the minus sign is a matter of direction, and we already determined the direction by the fact that the positive and the negative are attracted to one another. And for one, in the case of the negative charge is going this way, and in the case of the positive charge is going that way. And so for one it's a positive direction, for one it's a negative direction. So how can you put a negative into that magnitude? So what I suggest is, when using this Coulomb's law, is just find the magnitude first and determine your direction by our rules of thumb for charges. Positives and both negatives repulse, and unlike charges attract. Set up your directions based on that, find your magnitude, and then you've got your vector. Same thing for the case of the positive charge here and the negative charge over here. There's going to be attractive force between the two. For the positive charge, it's going to be in the positive x direction. For the negative charge, also in the negative x direction, because they're attracted to one another. The magnitude of that force is going to be 9 times 10 to the 9. 1.5 microcoulombs times 2 microcoulombs over 2 centimeters, 2 times 10 to the minus 2 meters squared, which would be 67.5 newtons. So here's our three forces. If we want to find the net force on the 6 microcoulomb charge, we find vectorially that one force is going one way and the other force is going the other way. And so whichever force is the largest is going to win. F1 is bigger, so F1 minus F2 is going to be our net force. 90 minus 43.2 is 46.8 newtons, and it's going to be residing toward the left in the negative x direction. So that will be our net force on the 6 microcoulomb charge. On the 1.5 microcoulomb charge, we've got two forces on it, F1 and F3, and they're both in the same direction, in the positive x direction. So we have F1 is 90 newtons, F3 was 67.5 newtons, so that's 157.5 newtons to the right. On the 2 microcoulomb charge, the negative 2 microcoulomb charge, we've got two forces off to the left, and that's going to be 43.2 plus 67.5, which will give us 110.7 newtons to the left. So we decide our direction based on what our vector forces add up to be. So all that stuff, force stuff that you remember from Chapter 5 in Physics 1, all that stuff that you know and love from that chapter has come back again. But it's just a force. So it's just a new force in town, and that's all you have to deal with, is new vectors and add the forces like you've done before. Here's another problem. In the Bohr theory of the hydrogen atom, an electron moves in a circular orbit about a proton, where the radius of the orbit is 5.29 times 10 to the minus 11 meters, approximately half an angstrom. Find the magnitude of the electric force and the gravitational force between these two particles. I don't know why we deal with the Bohr theory of the atom as opposed to the more interesting theory of the atom. We have the boring theory of the atom. That's just the way we go. All right, bad joke. Bohr theory actually is a good theory for the atom, even though it's approximation. You basically have the proton in the center, the electron going around in the circle around the proton. It's the simplest theory of the hydrogen atom. It works pretty well as approximation, even though we know that the electron is going around in an electron cloud like a sphere around the proton, but this more or less works. So we want to calculate the electric force in the simplest theory and simplest atom possible, with the one proton and one electron going around it. We have, that should be our K electric, charge on the electron, which is E, charge on the proton, which is E, over the distance between them square, which is the radius of the atom, half an angstrom. So this is going to be equal to 9 times 10 to the 9, and each of them have the same magnitude charge, 1.6 times 10 minus 19 coulombs. So we square that over the distance between them, which is the radius of the atom, 5.3 times 10 minus 11 meters, square that, and we get a force of 8.2 times 10 minus 8 newtons. That is the electric force between the proton and the electron in the simplest atom. What about the gravitational force between these two particles? Well, that force formula from Physics 1 is equal to the gravitational constant, mass 1, mass 2, in this case the mass of the electron, times the mass of the proton, over the distance between them squared. Look how similar the gravitational force is in terms of the design of the force. You have a particle times a particle over the distance squared times a constant, and that's the same form of the force for the electric force. We're going to try to make these analogies quite often between mechanics and the electrodynamics. In this case, the constant is 6.67 times 10 minus 11. The mass of the electron is 9.11 times 10 to the minus 31. Everything rhymes here. The mass of the proton is 1.67 times 10 to the minus 27. They rhyme, but they're not good rhymes. Over 5.3 times 10 minus 11 squared. That is a force of 3.6 times 10 to the minus 47 newtons. If you were to take the ratio of the electric force to the gravitational force in the simplest atom, you would find that the electric force is greater than the gravitational force by a factor of 2 times 10 to the 39. Wow. What does that mean? That means the electric force in the atom is stronger than the gravitational force between these two particles by a factor of 2 times 10 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 times 10. 39 times. Wow. So the electric force really is the force that holds atoms together. The nucleus with the electrons. The gravitational force is insignificant compared to the electric force that holds atoms together. This is like comparing the size of an atom to the size of the universe. It's that kind of comparison. If the electric force causes the centripetal acceleration of the electron, what is the speed of the electron? So this is a good model for the atom, the Spohr model. And we're going to say that the electron is going around in a circle, and the centripetal force is the electric force that we just found. So the mass times centripetal acceleration, v squared over r, should equal that electric force. And we can solve for the velocity of the electron. So that's going to equal the square root of the electric force times the radius of the atom over the mass of the electron. That's going to be 8.2 times 10 minus 8 newtons, 5.29 times 10 minus 11 meters. Mass of the electron, 9.11 times 10 minus 31 kilograms. All that square root. We find the electron is moving at a speed of 2.18 times 10 to the 6 meters per second. The speed of light is 3 times 10 to the 8 meters per second. So this is almost 1/100th the speed of light. So we're talking about an atom, which is extremely small, and on the size of the atom on the order of 10 to the minus 10 or so. So the electron is moving around this proton in that very small confined space in a sphere at a speed of about 1/100th the speed of light. So that's one reason why you can never locate where the electron is. It's moving so fast in such a small area that you never can be sure exactly where it is. And that's why that brings up a whole new study of physics called quantum mechanics, in that the only way you can really study such an object is with probability. You would say, there's 60% electrons over here and 40% over here, because there's no way you can ever possibly locate it exactly where it is. The electric field, in an analogy to a gravitational field where force equals mg, the force in an electric field is equal to QE, where Q is the charge and E is the electric field. So you have the object, like a mass, times the field, mg, but here's Q times the field. That is the force on a charge in an electric field. Actually, the formal definition of electric field is based on this idea. You would say that the electric field is the force per charge that exists in some volume of your environment. Kind of like the gravitational field, which is the force per mass in some volume of an environment as well. In fact, that's how you define the gravitational field. Let's say I want to find out if there's a gravitational field right here in front of me. The way I would do that is I would bring in a mass like this, and I would let go and see if there's a force on that mass. Ah, yes. Since there was a force on that mass, I would measure that force, divide it by the mass, and that defines the gravitational field in that vicinity. I would do the same thing with an electric field. With an electric field, I'd bring in a charge, let go, and see if there's a force on that charge. And if there is, the value of that force divided by the value of the charge defines the electric field. So that's how we do it. If it doesn't move, then there's no electric field there. Here's a problem. An object having a net charge of 24 microcoulombs is placed in a uniform electric field of 610 newtons per coulomb directed vertically. What is the mass of this object if it floats in the field? So in this case, we're going to have an electric field going up, and hence, since the object has charge, there's going to be electric force going up as well, and that's going to balance with its own weight if it's going to float. So we'll have an electric force of QE going up, balancing against a gravitational force of mg going down. If it floats, we can use these forces. They should be equal in magnitude. So QE will equal mg, and based on this, we can solve for the mass of this object. So the mass will equal QE divided by g. The charge was 24 microcoulombs. The field was 610 newtons per coulomb, which will be force per charge, newtons per coulomb. G is 9.8 meters per second squared. Everything is SI units. So our mass is 0.00149 kilograms, or about 1.5 grams. This is really a similar method to what Millikan did in his oil drop experiment. He had the oil drops, which he knew what the mass was of them, and he would suspend them in the field, and he knew what electric field and voltage he was applying. So based on that, he could figure out what the charge was on each suspended oil drop, and that's how he found that the charge was discretely found in definite intervals between each suspended group of oil droplets. Very ingenious. All right, so we've defined the electric field, and in fact, an electric field producing device is indeed a charge itself. A positive charge emanates electric field radially outward in all directions, three-dimensionally in all directions. Whereas a negative charge has electric field lines coming in, terminating on the negative charge, radially inward from all directions, three-dimensionally. So, positive charge emanate electric field lines, negative charges terminate electric field lines. The density of the field lines will indicate the strength of the field. So if I want to indicate that the electric field is stronger, I would just draw more arrows, more red arrows, and the density of those lines would indicate that the field was stronger in that vicinity. And if the field were weaker, I would just draw less arrows, erase some, and the density of those arrows then would indicate that the field was weaker. So consider a point charge emanating an electric field in all directions. And in particular, we have a unit vector here indicating the radial direction away from this point charge. We define the electric field for a point charge as being equal to our K electric constant, 9 times 10 to the 9, times the charge over the distance squared where the distance is the point at which we're evaluating the field. So at some distance r away, the field is equal to kq over r squared. The r hat here is just simply giving us a radial direction. So that all that is a unit vector showing us the direction that we're going. So the key part here is the kq over r squared. That's the magnitude of the electric field at that point. Now, if I were to bring a second charge and place it at that point, it's going to feel a force due to this electric field from the first charge. The force it feels is going to be equal to the value of that charge, Q2, times the field that exists there due to the first charge. And the field that exists there due to the first charge is kq1 over r squared. So we'll have the force is equal to Q2 times kq1 over r squared, and that's going to equal kq1 q2 over r squared. By golly, that's the Coulomb force that we introduced earlier. So now we're saying that a charge produces an electric field that another charge can experience. And if it does experience that, it will feel a force, and that force is the Coulomb force. It happens the other way as well. Q2 creates an electric field experienced by Q1 equal to kq2 over r squared, and then the force Q1 feels is Q1 times that field, which is the same value of Coulomb's law. Let's say we want to find the electric field at some point, and we have a bunch of charges around. What we would do is find the electric field due to each charge separately, individually, in a vector sense, magnitude and direction at that point. And if it were positive charges, it would be emanating radially away from the positive charge along that line of action from the positive charge to that point. And if it were a negative charge, it would be coming in, terminating towards a negative charge along the line of action from that point to the negative charge. But we would find all these vectors, magnitude and direction, and then we would add them up vectorially to get our net field that exists at that point. That's the principle of superposition, and basically it's just saying find all the individual contributions, add them together vectorially to get our net field that exists at the point. And if we did that, we could map this whole field everywhere in three-dimensional space in the vicinity of these charges. Here's kind of an example. Here we have a positive charge, and we have the electric field lines emanating away from this positive charge, radially away, indicated by the red arrows. The blue dashed lines are indicating something else that we're going to introduce later. They're actually lines of equal potential or equal voltage, and that's going to be something that we're going to use in Chapter 25. But for the moment, think about the red lines. If I brought in a negative charge where red lines E field are terminating on the negative charge, if these two were close together like this, their E fields would add together, superimpose together, and we would see this kind of configuration. And we can see that between the positive and negative charge, the E field is denser right in the vicinity between the charges. Hence, the E field is greatest in that vicinity, and then it gets less and less dense as you get further and further away. This actually is a famous configuration of charges called a electric dipole, where you have a positive and negative charge close together like this. Okay, we want to conclude this first lecture by a few extra ideas. And one is the idea of induction. We can induce a charge on a conductor by bringing another charged object into close proximity to the conductor. In this case, we'll say the conductor is normally neutrally charged. It has as much positive charge as it has negative charge. But if you bring in, say, a rubber rod that's been negatively charged, it will push the other negative charge away. The like charge will be repulsed, and in a sense, the positive charge will be attracted. Even though the positive charge doesn't move, the movement of negative charge will essentially move positive charge towards this negative charge here. If you allow this negative charge to escape, you can leave this conductor with a net positive charge. As you take away your ground here, that net positive charge will find itself as far away as possible it can from the other positive charge, because like charges repel, and hence this positive charge will find itself as far away as possible and actually will reside on the surface of that conductor. But you will leave that conductor with some net positive charge in this particular case. That is induction. You can also induce charge on an insulator. Charge on an insulator is locally owned by what are called domains, in a sense, electric domains. And if you brought in a charged object, a positive charge, you can reorient those domains so that the like charge is repelled and the unlike charge is attracted. And so you just orient those domains in such a way that you induce a charge towards the surface of that insulator that would be preferentially of some value, in this case negative. So you can induce that on a insulator that way. Here's another idea that we wish to conclude with, and that is the idea that if you have a force on a charge or an object, then there should be an associated acceleration. And if your force is constant, which we're looking at a new constant force, then your acceleration will be constant. And all the ideas, all the treatment that we had from Physics 1 dealing with forces and acceleration will apply again, namely kinematics. Here's our problem. We have two charged plates, and we'll prove later that if you have two charged plates like this, the E field between them will be a constant value. So that will give us a constant force on any charge placed between these two charged plates. So the net force associated with this E field, this electric field, will be equal to this one force, QE. And so by Newton's second law, mass times acceleration will equal charge times field. In other words, our acceleration will be equal to the charge to mass ratio times the field. If you have a particular charge and it has a particular mass, the value of the charge and the mass will be constant. And if you place it in a constant field, that will be constant. So our acceleration will be constant. And all the kinematic equations that deal with constant acceleration will apply to the motion of this particle. So our usual kinematic equations that you know and love from Chapter 2 in Physics 1 have come back again. All those 5 kinematic equations dealing with constant acceleration apply to the motion of this charged particle. The only thing you need to add to this is that the acceleration is q divided by m times e. Once you calculate the new acceleration, the motion of that charged particle is governed by the 5 kinematic equations. We can deal a lot more with this, but basically that's the way to approach these problems. Just define your new acceleration based on the E field, and then use the kinematic equations that you know and love from Chapter 2. We'll look at a few examples of this in the education problem examples online. Here's an application of this. In the old style oscilloscope, cathode ray tube, you have an evacuated tube that is there's no air in there, so that charged particles can move freely without colliding with air molecules. And if you put plates in there, you can deflect your charged particles. And if these plates are a constant E field, then you can deflect them a definite amount based on how much voltage you apply to these plates. You could do that vertically, and you could do that horizontally, and by doing that, you could force this charged particle to hit anywhere you want on a two-dimensional screen. If the screen is fluorescent, then it will light up where your charged particle hits. And that's the basic idea behind an oscilloscope. Now, on an oscilloscope itself, your horizontal plates will actually be fed a sawtooth voltage form, and the sawtooth voltage form, looking like a triangle like this, will force your scan to go across the screen at a consistent time movement. So the sawtooth voltage form will just make you sweep across the screen consistently, and then whatever you're measuring will go on your vertical. And if you're measuring like a cosine function, then it will look like a cosine or a sine sinusoidal function across your screen, and you can measure that using this device called the oscilloscope. Your old TV sets were somewhat like this. They were cathode ray tubes, and when you hit the screen, there actually were different colors, red, green, RGB, red, green, or blue, and depending on how many pixels you hit, you could actually form a nice image, color image, which if you were far enough away from the screen, they kind of blend together and it will give you a nice color image on the screen. If you got up close, you could actually see all the different pixels of the red, green, and blue on those old style TV sets. This concludes the first lecture in Chapter 23 dealing with electric charges and electrodynamics.